Thank you very much for having me. I'm Benjamin Zhang. I'm a first-year PhD student at the University of Southern California. I'm going to be talking about some work I recently submitted with KJ Lee at Kavli IPMU, and also working with Ben Horowitz, who are both here. And I'm going to be talking about alignments between galaxies on the cosmic web at redshifts of 1 to 2 using the IllustrisTNG simulation suite. Yep, so just a really quick overview of what I'm going to be going over. I'm going to be going over the background of galaxy cosmic web alignments just super quickly, since everybody's familiar with it. Then I'm going to be talking about the simulated alignments we found in the IllustrisTNG hydrodynamical simulations. And finally, I'm going to be talking about extending that to a mock observational survey for detecting these alignments modeled off the upcoming Subaru Prime Focus Spectrograph survey, or Subaru PFS, as I'll be calling it for short. So just, again, a super quick overview of galaxy cosmic web alignment, since we're all familiar with it. Basically, since galaxies are forming from the cosmic web, tidal torque theory and tidal stretching theory predicts that basically galaxies will form with non-random alignment of their angular momenta and the orientations with the cosmic web filaments, walls, etc. This, in turn, creates what's called intrinsic alignment between galaxy pairs on the sky, which is an important nuisance parameter to characterize for weak lensing. However, for the remainder of this talk, I'm not going to be talking about intrinsic alignment when I refer to alignment. I'm going to be talking about direct density and galaxy alignment only. So just going over some results we expect from previous works. Mostly I'm going to be looking at works looking at simulations. So looking at the alignment between kind of longest axes of galaxies, or the orientations, which I'll be calling shape alignment, and the cosmic web. Here, we're using the Hessian kind of formalism for the cosmic web. So this is kind of the filament direction. We expect that galaxies are aligned more parallel with the cosmic web. Their shapes are. And we expect that as their stellar mass increases, that the strength of this alignment kind of monotonically increases. By contrast, as Christophe outlined in his talk on Monday, when we're looking at the alignment between angular momenta and the cosmic web, we see that there's actually a flip between parallel alignment and perpendicular alignment at a particular stellar mass here, which simulations have found to be in around this stellar mass range. However, on the observational side of things, we expect this alignment to kind of get stronger as we get to higher redshift, because like less mergers have happened at higher redshift schematically. However, observationally, not too many attempts have been made, because it's hard to reconstruct the cosmic web conventionally by using galaxies as density tracers. However, Clotilde did talk about her work doing this for redshift 1 on Monday. But however, for redshifts of 1 to 2, the Subaru PFS survey is going to be very well placed to constrain this alignment for reasons which I'll be talking about in a little bit. So next up, I'm going to be outlining the results for alignment we found by looking at the IllustrisTNG simulations. So just going over the data we used the IllustrisTNG hydrodynamical simulation suite. We used the run, which had a 200 NPC/h box length, and a better mass resolution run to kind of check the consistency of this signal with regards to kind of the resolution of the simulation. For both of these, we looked at the snapshots at redshift 1 and redshift 2. As I mentioned before, we're using the Hessian formalism for characterizing the cosmic web, where we take the Hessian of the gravitational potential, which we're calling the deformation tensor, and look at its eigenvectors. And we know that the convention we use, which is kind of opposite from other works, is that we call the eigenvector of the most negative eigenvalue the E3 eigenvector. Some other works call it the E1 eigenvector. So for the galaxies from the simulation, we compute the orientations, which we'll call the shape, and the angular momentum, which we'll call the spin. And for both, we impose sufficient cuts to make sure that the galaxies are kind of well defined, that we're not computing this for just a galaxy composed of a few particles. And again, we do this for each simulation, for each sub-simulation with different box lengths, and for each sub-simulation, we do this for both redshifts. So first, looking at our results for alignment between shape and the cosmic web at redshift 1. So how to read this graph is basically, here we're looking at the alignment, the cosine of the alignment angle between the cosmic web eigenvector and the shape of each galaxy. What we're doing here is we're taking a bin in log stellar mass space. For the bin of this size, we compute basically the mean of this cosine, which I'll be calling the mean alignment. We plot that here in the center with associated errors from bootstrap sampling. We take that bin and then we slide it over basically in log mass space to get kind of a continuous record of how this mean alignment is changing as we kind of increase the stellar mass of the galaxy sample. So what we see is that looking at the alignment with kind of the E3 eigenvector, which again is kind of the cosmic web filament direction generalized, we see that we get the results we expect from previous works in that the shape alignment strength is line parallel and that it's increasing kind of monotonically with increasing stellar mass. So since observationally we're observing this kind of high mass end, i.e. bright end, this gives us good observational prospects for actually measuring this in reality. And we see the same thing for redshift 2 as well. However, an interesting result is that when we actually look at the alignment between spin and the cosmic web at redshift 1, we don't see any kind of very significant spin flip where we're going from parallel to perpendicular here. And in general, the magnitude of the alignment we see is much less than has been seen in previous works working with other simulations, in particular the Horizon AGN hydra simulation. And the same thing for redshift 2 as well. So just comparing this with Horizon AGN directly, Clotilde showcased this in her talk on Monday as well. If we basically plot the same mass range in IllustrisTNG as was plotted in Cody's paper in 2015 using Horizon AGN for Galaxies, and in addition, this is using the same cosmic web formalism, the Hessian formalism, we see that the strength of the spin alignment between IllustrisTNG and the cosmic web is much less than Horizon AGN here in black. Specifically, we calculate that it's around 2.4 times weaker. And this suggests that kind of alignment still has very significant dependence on the detailed physics of the simulations, and it hasn't really converged between simulations. So Clotilde also gave like a better overview of this in her talk on Monday.
What's the smoothing scale?
So the yes, I forgot to mention that. The smoothing scale we're using is 2 MPC over H for the density before we calculate the deformation tensor. Yes, that's true. Okay, so for the next part of this talk, I'll be talking about kind of how we can extend this to observational studies, i.e. When looking at Subaru prime focus spectrograph, how well we can measure the alignment we're seeing in the simulations. So just a really quick overview of Subaru PFS. Ben Horowitz gave a good overview of this in his talk. Basically, Subaru PFS is a spectrographic survey soon coming online, which will be getting a lot of spectrographic redshifts at a wide redshift range of around 0.7 to 7 or so. But we're going to be focusing on the galaxy evolution subprogram at this redshift range of around 1 to 2.5, where the pertinent points are that at around a redshift of 1.2, we're going to be getting around 250,000 species. And at around redshift 2.3, we're going to be getting 15,000 or 30,000 species, depending on the precise allocation of time. And in addition, we're going to be getting independent reconstruction of the cosmic web by using IGM tomography. So if we want to study the alignment between cosmic web and shapes, we have to match galaxy shapes from near-IR space telescope imaging. And in addition, because at these high redshifts, it's not really possible to resolve the morphology of galaxies. In order to kind of estimate the angular meta, you need a kind of deep IFU spectra to do that, which is a little bit unfeasible for this large of a sample. So for everything onwards, we're only going to be considering alignment between shape and the cosmic web. So just super quick words about IGM tomography. Ben Horowitz gave a really good overview of this in his talk. But the gist of it is that since density reconstruction conventionally from galaxies is really hard, for redshift 2, we kind of need IGM tomography, where the Lyman alpha force traces, the density of neutral hydrogen coming at us along this kind of skewer from a background object, usually an LBG or a quasar. This has been done by KG in the Clamato survey in the cosmos field. However, Subaru PFS is going to be probing a much larger volume for this. And the upshot of it for our purposes is that basically, if you use Ben's TARDIS code to reconstruct the cosmic web from IGM tomography, you're able to reconstruct the cosmic web eigenvectors, the Hessian eigenvectors, pretty accurately if you look at this red line for the PFS forecast. Okay, so actually an interesting thing we found while trying to do this mock observational survey, and this might address a question that was asked in the previous talk, is that we actually found that since we're unable to observe kind of the full 3D shape to cosmic web alignment, we can only observe kind of the shape of the galaxies projected onto the sky and their alignment with the cosmic web. We find that since we're measuring this, what I'm going to be calling 2D alignment, that the kind of perspective you have on the kind of galaxies on the sky, in our case, the perspective you have on the simulation volume, has a fairly significant effect actually on the alignment signal you measure. So if you consider, say, this like kind of toy example I have on the bottom, where say you have a relatively small volume that's dominated by kind of a single cosmic web filament running through. Now, if you consider kind of the 2D alignment between that filament and the associated galaxies, because the galaxies are aligned with the filament in 3D, so say if you're looking at this box side on here, you will compute a very strong 2D alignment between the filament and the galaxies, because the galaxies being ellipses are kind of, the shape are well preserved by projection onto the sky. However, if you happen to be looking at it like head on, say here, down the barrel of the filament, you'll find that you're computing a much, much weaker alignment because the shapes kind of don't project well and neither does the filament project well onto the sky. So we're finding that even if we scale it up to this kind of 300 MPC simulation box that we're using for the mock observational survey, that this effect is actually still pretty significant, which gives us a possibility of kind of a cosmic variance induced false negative when we actually do this in observations. So in order to characterize this, what we do is when we're constructing this kind of mock observational pipeline, we adopt this kind of what I'm calling a viewing angle agnostic approach, where basically for a bunch of viewing angles onto the simulation volume, kind of evenly spaced over the sky, we do the following. We have this galaxy sample from IllustrisTNG, which we select using abundance matching with simulated magnitudes, though we don't have any kind of realistic dust extinction. And we also have the true density here, of course, the true cosmic web. For each of these viewing angles, we construct a different mock observational survey with the same parameters as Subaru PFS. So basically, we take IGM tomography skewers along the line of sight of the viewing angle, and we also perform redshift space distortion on the galaxy positions along the line of sight, along the viewing angle's line of sight. We run this mock observational survey through Ben's TARDIS code to get a reconstructed cosmic web. And we also take the redshift space distorted galaxies, and we project kind of their shapes onto the plane normal to the viewing angle. And we do the same with the cosmic web eigenvectors. So because we have this kind of sample which is kind of marginalized over all these viewing angles, when we compute the errors on the shape alignment we see using bootstrap sampling, we're actually bootstrapping over both the galaxy sample and over all of these viewing angles. So the errors that we calculate include the errors we get from performing RST on different viewing angles, reconstruction using data along different viewing angles, and also importantly, the effect we discussed before, where basically the fact that we're projecting onto different planes normal to the viewing angles induces a pretty significant variance in the alignment we see. So our results here, if you look at kind of the right half of each panel here, where we're computing the alignment between shape and the cosmic web eigenvectors, again, this is projected onto the sky at redshift 1. We see that because we have a large galaxy sample and our density reconstruction from TARDIS is pretty accurate by using kind of just this large galaxy sample. We're not using IGM tomography for redshift 1. We're able to detect the 2D shape alignment pretty significantly with the overall kind of significance if we total all of these eigenvectors together and subtract from the mean of around 5.3. However, our picture is more pessimistic at redshift 2, where the fact that we have a smaller spec-Z sample and also more uncertain density reconstruction compared to redshift 1 means that our overall significance for shape alignment we detect is around 1.3 sigmas, and this doesn't improve by much if you increase the spec-Z sample to around 30,000. However, as we noted before in the simulated alignment section, in IllustrisTNG, we're seeing a much weaker kind of overall signal than we saw in Horizon AGN. So basically, in reality, if our kind of ideal alignment signal is around the same strength as Horizon AGN, if we do this extremely rough estimate and just kind of multiply the alignments we see by how much stronger they are in Horizon AGN when compared to IllustrisTNG, we find that we may be able to detect the redshift 2 shape alignment signal with a good significance over the conventional barrier of 3 sigma. But in addition to those challenges, we actually have another bottleneck if we actually want to do this observationally, in that we need the galaxy shapes in order to match kind of with the cosmic web. So because we're working at really high redshifts, we need to be able to resolve the galaxy shapes very well, and that requires high resolution near our images, which in turn requires that these come from the space-based telescopes. So right now, our source of data for that is HST. However, it only covers a small portion of what Subaru PFS will cover. Roman Space Telescope should cover the full footprint, but only post kind of late 2020s. So in summary, takeaway points is that Subaru PFS is well placed to be able to constrain these cosmic web and galaxy alignments at high redshifts. Surprisingly, we find that the alignments we see in the IllustrisTNG simulation, discounting any observational effects, are much weaker than we find in other sims such as Horizon AGN, which suggests that this signal has not really converged between simulations. It still depends on the detailed subgrid physics. Observationally, we find good prospects for constraining this at redshift 1, however, less so at redshift 2. But again, this depends on what the kind of alignment signal is in reality, whether it's closer to what we see in IllustrisTNG or closer to what we see in Horizon AGN. But in any case, we're going to need a lot more high-resolution galaxy imaging in order to do this observationally. So yeah, that's it. Thank you very much.
Questions?
Have you considered trying to find a spin flip signal in the dark matter component? Because you're blaming subgrid physics, but...
Yes. No, we haven't actually looked at the dark matter component, but that would be a good idea.
Because it's much clearer, right?
Yes.
And another related question, have you considered using the same filament detection algorithm? Because all the algorithms which are based on eigenvectors of the whatever have a bias towards nodes, in the sense that you can only have one filament going through a node if you only expand the field up to second order in its derivative. So that might have an impact. So it would, before you blame subgrid physics, you should make sure that all the other things are...
Yes, of course.
But the comparison for
Yes.
The comparison with Kavli is one-to-one.
No, Codis uses the skeleton.
I think in this Cody's paper, they're actually using the Hessian formalism instead of the skeleton. Though in a lot of Cody's papers, she does use the kind of dispersed skeleton.
Yeah, so this paper does use the Hessian.
I doubt it, but I'll check.
I have a question for a second. So just terminologically,
Yeah.
you're talking about deformation tensor.
Yes.
What exactly for you deformation tensor is?
So I think what I'm referring to as the deformation tensor is what other people at this conference have referred to as just taking the Hessian of the gravitational potential and diagonalizing.
Potential. Yeah. So your first slide was saying that in this talk you are only speaking about alignment between galaxies and density.
Yes.
But deformation density isn't density,
I see.
right? You need to make a step back to find out what deformation tensor is. It's not derivable from density. So,
Yeah, sorry.
So how do you find deformation tensor in observations?
So in observations, basically using Ben Horowitz's TARDIS-2 code, we're able to get a reconstructed dark matter density field, and from that we can calculate the deformation tensor.
So you reconstruct potential and then you
Yes. Yeah.
I just had a quick question. I thought TNG 100 was with gas, but then you talked about using abundance matching. I didn't understand. Were you adding in an extra, or did I just mishear you?
So I believe both TNG 300 and 101 include gas. They're like full hydrodynamic physics. I guess what I mean by abundance matching is that we just kind of did a simulated magnitude cut along the kind of same magnitude band we expect Subaru PFS to select, and that's how we selected a portion of the galaxies in our sample.
Okay, great, thanks.
Thanks for the talk. So it seems to me like there's like a few, like a little bit disagreement between TNG 100-1 and TNG 300-1. So wondering if you also looked at like, different resolution versions of the same simulation, right? Like TNG 100-1 and TNG 100-2, and if there's like a similar level of disagreement. So whether or not you can chalk this up to resolution.
We think that in the case of disagreement between TNG 301 and 101, it's probably kind of cosmic variance on 101's part, but I'd agree that it would be a good idea to look at different resolutions of kind of the same box length. Yeah.
Well, I have one more obviously trivial question. So at some moment you said that you're actually working in a projection.
Yes.
So what does it mean, 3 eigenvalues in projection? Or 3 eigendirections?
So it's literally just taking kind of the 3 orthogonal eigenvectors at each point from the deformation tensor and then just projecting it onto the plane normal.
So you define them in 3D and then you project?
Yes.
And you do the same with observations?
So we're only doing this in observations. In the previous section, we were looking at the 3D alignment, so no projections.
I think the point he's making here is that you basically don't just pick the standard XYZ in a simulation. He goes through many directions, and each direction he does the correct thing.
But I'm trying to see what the 3-dimensional structure projected in projection means.
No, that he just means that they're calculated according to the correct, like rotated axis.
So let me invite the next speaker to actually set up the machine. And if there's no more questions, we'll thank you very much.